We're going to be talking about transformations of data today. Okay, first we're going to talk about, okay, why even transform data? Then we're going to talk about two different broad types of transformations, shape-preserving and shape-changing transformations. Then we're going to talk about some common shape-changing transformations that you might need to know. Some of them you actually already know. First, why transform? Well, one of the big reasons to transform data, especially in a shape-changing way, is that all that stuff with regression and correlation and all that stuff we've been learning, it really only works for linear patterns. If your pattern isn't linear, even though you can still fit it to a regression line and you still can find correlation, it probably isn't the best way to go because, for instance, in this graph, you could see like this has a distinct sort of curvy shape, right? And so a simple linear regression won't account for a lot of this this variation, not as well as a curved line would. Sometimes the transformation might make a nonlinear pattern more linear, thus making regression and correlation more useful. All of a sudden, you can use regression and correlation, and it will account for a lot of the data. And so that might be one reason to do that. So let's look at this data, for example. This is data that we've looked at before from gapminder.org, where it shows the income per person in GDP per capita. So it's so take all the stuff that your country buys and sells, right, and divide it by how many people you have, right? And it shows life expectancy here. And notice that it says lin, and this is a linear graph, right? So it's just showing you even intervals. So the distance between 10,000 and 20,000 is the same as the distance between 60,000 and 70,000. Same here, the distance between 55 and 60 years old is the same as the distance between 80 and 85. But one of the issues with this is that it has a distinctly curved shape. Primarily, it's that a lot of countries are very, very poor in terms of GDP per capita. They're very poor, and they're all clumped together sort of over on this side. So most countries make less than about 15,000 per person. So they're all sort of squished over on this side. It would be really nice if we could somehow like stretch out this part and maybe squish those down, because these countries are all probably very similar because they are all like fairly rich countries. A lot of them are in Europe, and this is probably the United States, right? So because of that, that might be nice. One way we could do that is we could do a log transform. So instead of giving us the income per person, we could look at it on a logarithmic scale. And if you remember log is like, I always remember it like, okay, I have to actually like say it out loud. Log is like let's say log base 10. So that means 10 to that power, right? 10 to the answer's power will give you that number x. So if we have log 10 of x, right? So 10 to the power y will give us x, right? So I always have to say it out because it's sort of like this loopy idea, right? This is instead of plotting the actual x's, it's asking, oh, maybe we could transform this so that it's giving us just the exponents, right? So the way you could do this is show this on a logarithmic scale. And now the first parts of this are sort of stretched out, right? So the distance between 400 and 1,000 is really big. And that's actually bigger than the distance between 20,000 and 40,000, right? So that's a logarithmic or exponential scale, right? So here we see the same data, except now we've taken we're plotting it by the log of these scores, right? Of these incomes, and here what we see is a more linear pattern, right? So before we saw sort of a curved pattern, but now we see roughly more of a linear pattern. And so that's one reason why transformations are very, very useful. All right, but there are two kinds of broad transformations you should know. One is shape-preserving transformations, and the other is shape-changing transformations. Shape-preserving transformations is something where you don't actually do anything to the distribution's shape. The shape looks the same. So if we looked at a scatter plot, that scatter plot would look exactly the same. It would, if it's linear, it would stay linear. Shape changing means that if it's linear, maybe we make it curvilinear. If it's curvilinear, we make it maybe more linear, right? And so those are shape changing transformations. In order to be shape preserving, this means that these are any linear transformations. And remember, the equation for a line is y equals mx plus p, right? And this is like the classic formula for a line. Anything where you add a constant or you multiply by a constant, those are called linear transformations. But shape-changing transformations are anything that's nonlinear. So now you need to do something more than adding by a constant or multiplying by a constant. So that might be, changing x into an x squared, or taking the square root of x, or adding in other variables, right? So adding in another variable here. So z, right? So these are nonlinear transformations. So this is anything where you do beyond just adding or subtracting or multiplying and dividing by a constant. So here are some common shape-preserving transformations. These are ones that do not change the shape at all. When you add and subtract a constant, that's fine. If you multiply or divide a constant, that's fine. Converting units is often a common shape-preserving transformation. For instance, we collected our data in feet, but we want to see it in inches, or something like we looked at minutes, but we really want it in hours, right? So there we're just multiplying by a constant. Here we're multiplying by 12. Here we're dividing by 60, right? And so those are shape preserving. You'll have the same shape. Another shape preserving transformation is standardization, or finding the z-scores. When you find the z-scores will have the same shape as your raw scores, because we're subtracting by a constant, right? Subtracting by x bar, or the mean, and dividing by a constant. So you could do combinations of these two things and still have a shape-preserving transformation. Another common shape-preserving transformation that you might want to know are transformations from frequency to relative frequency. So that's also shape preserving, where you might have, just raw number of people, but you might also want to have proportion, right, from the total, right? So that's another way, because remember, finding relative frequency, it's often just dividing by a constant. So those are shape preserving transformations that you've already seen. Now, shape-changing transformations, the most common ones used are power transformations and log transformations. Power transformations are anything where you raise your y or x by some power. So, for instance, from y, you change it into y squared, or y into the square root of y, or dividing 1 over y, right? So, so raising it to the negative power, right? So any of these and any combination of these is a power transform. Log transforms are finding the exponent, right? So instead of raising it to an exponent, it's sort of finding the exponent. So you could find the log of y, and this will give you smaller numbers, right? Or you could find the natural log of y as well. So any of these are possibilities. You could also look at things like e to y, so that's just the inverse of this. And also like some other constant to y. So you could use the exponential constant or just something else, right? Alternative, although I've written y here, and oftentimes you might see y become transformed, but it's also quite common to transform x as well. And sometimes you might transform both, right? You might transform both y and x, and we'll talk about those situations as well.